Okay, so we start looking at just a simple circuit here where we have a sinusoidal source, an AC source, and a simple capacitor in a circuit here. So when a sinusoidal voltage, V sub S, is applied across a capacitor, the voltage waveform has a maximum rate of change of dV by dt. So the expression here is telling us it goes max, okay? So if we look at the corresponding waveform, the maximum positive of the rate of change then, you can see is at the crossing line at 0. At the top where we have maximum voltage though, we have 0 rate of change. So the voltage waveform has a maximum rate of change then from here going to 0 here at the 0 crossing point. The 0 rate of change dV by dt then is at the peaks. So whether it's positive or negative. The phase relationship then between the current and the voltage for the capacitor then is defined by the expression that we just developed. The instantaneous current I, you could say I of t, is equal to the capacitance times the rate of change dV by dt, or as the voltage changes with time. When dV by dt is equal to 0, the current is also 0, because when we put in the expression here, dV by dt is 0 times the capacitance, we get 0 as our result. So this is just, don't let this throw you. It's not really a fraction. It's just showing a rate of change, one with respect to the other, voltage with time. When voltage, dV by dt, is a positive going maximum, the current then is a positive maximum. When the rate of change of voltage by time is a negative going maximum, correspondingly, the current is a negative maximum. So you need to get this in your mind, what's going on here as the voltage changes, what the corresponding current is doing at the same time. A sinusoidal voltage then always produces a corresponding sinusoidal current. So they go hand in hand. You'll get one waveform that's AC voltage. You'll get another that is AC current. Although the term AC says alternating current, it's a sinusoidal voltage and a sinusoidal current. The current then can be plotted with respect to the voltage by knowing the points on the voltage curve at which the current is 0 and those at which it is maximum. So you can see here we're starting to develop this relationship, the voltage across the capacitor as it varies with time. Okay, one single sinusoidal cycle here. You can see the corresponding current then is showing us that when voltage is 0, current is maximum. When voltage is maximum, current is 0, and it progresses. So we can say then, using our phasor relationship, current on the vertical axis, voltage on the horizontal axis, current always leads the capacitor by a voltage of 90 degrees. So you can see this relationship. It bears out with the instantaneous sinusoid that you can see on the left. So that leads us then to come up with a relationship that we need to have to develop what's happening resistance-wise in a circuit, in a capacitive circuit. And correspondingly, we use something called the capacitive reactance X sub C. So the capacitive reactance is the opposition to sinusoidal current, and guess what? It's expressed also in ohms. So we don't need a new term, although we do have something called the capacitive reactance. Its measurement, its units are in ohms. So the symbol for capacitive reactance we say is X sub C. X for the reactance, sub C meaning capacitive. We'll do the same thing with inductors. To develop the formula X sub C, we use then that relationship that we started with. The current is equal to C, the rate of change dV by dt, and the corresponding curves here. So you can see here what's going on with curve A curve B, that we start to have and develop, there's our slope right there, we start to develop this phase change or this phase relationship. So the rate of change of voltage is directly related to frequency. We're going to see that over and over again. That frequency of the signal, the AC signal, the sinusoid, is going to tell us what the voltage, the reactance, and the current is going to be in a circuit. The faster the voltage changes, the higher the frequency. So there's a one-to-one relationship. The slope of a sine wave A at the crossings is steeper. Well, you can see here, A right there has a steep slope than the slope of B, which has a little less slope to it. Okay, the slope of a curve at a point then indicates the rate of change at that point. Okay, the instantaneous value really. Sine wave A has a higher frequency than sine wave B, as indicated by a greater maximum rate of change, or the slope. dV by dt is greater than at the zero crossings. So very quickly then, what we see here is that when frequency increases, dV by dt increases, and consequently I increases. Conversely, when frequency decreases, dV by dt decreases, and the current decreases. And we can see that here really quickly in these relationships then. Frequency increase, these values go up. Frequency decrease, these values go down. So an increase in current means that there is less opposition to current. So the reactance, X sub C, will be less. A decrease in current means a greater opposition to current, X sub C, will be greater. Therefore, X sub C, the capacitive reactance, is inversely proportional to the current and inversely proportional to the frequency. This is what comes in our mathematical relationships, understanding what we're looking at mathematically. If something is in the denominator, what we're expressing it as is inversely proportional. There's our little inversely proportional sign. So X sub C has an inverse relationship with frequency. Frequency goes up, X sub C goes down. So there's our quick mathematical definition. Okay, for current then, current is equal to the capacitance times dV by dt. We can see here as capacitance goes up, current goes up, the rate of change of voltage goes up. And inversely, the rate of change goes down, current goes down, capacitance decreases. Okay, so there's our introduction to capacitive reactance.